Hi folks, we're going to take a look at page 345, number 10. So what they want us to do here is to find the equation for the set of points equidistant to these two given points, and then they want us to find two particular ones. Okay, so the way they've posed the question, they're indicating that there's many points which will have the same distance from each of these 2 points. Okay, so I'm going to use a diagram just as a guide. Again, I'm not going to make any effort to make it an accurate diagram, because here I've got this point A, which is 2, negative 1, 3, and I've got another point B, which is 1, 2, negative 3. And all I want to do is I want to represent an example of a point which is equidistant to those two. Now, I'm not even going to use the nicest one, which would be just joining them by a line and finding the midpoint. So let's say here I've got some point which I'll call x, y, z, okay, my unknown, where the distance to each of these points is going to be the same. Okay, but let's think about how we can determine the distance between 2 points. Well, instead of thinking of it as a distance in between 2 points, think of it as the magnitude of the vector joining those 2 points. Okay, so if I form a vector there and I form another vector here, okay, if those 2 distances are the same, then the magnitudes of those vectors are going to be the same. Okay, so this is going to be my starting point for solving this problem. Now notice here how I drew the vector from A to P and B to P. The vectors PA and PB would also have the same magnitude. The reason I do that is because when we find the vector between 2 points, I always subtract second minus first, and I'd really like to have those variables in the front. Okay, so essentially what I'm solving is I'm solving the equation magnitude of AP has to be equal to the magnitude of BP. Okay, and since P represented an unknown point in R3, this should generate an equation that provides all possible answers. Okay, so let's do that. So first we'll find AP and BP. So here we've got AP. So again, remember second minus first. So we've got x minus 2, y plus 1, because you're subtracting negative 1, and z minus 3. Okay, and then on the other side, your vector is just going to be x minus 1, y minus 2, and z minus negative 3, so z plus 3. Okay, and now that we have our 2 vectors, we can find the magnitudes of each. Okay, so this is the square root, and we're just going to sum up the squares of the 3 components. So x minus 2 squared plus y plus 1 squared plus z minus 3 squared. Okay, and that's going to be equal to the other magnitude, so x minus 1 squared plus y minus 2 squared plus z plus 3 squared. Okay, I think pretty obvious that we're going to want to get rid of this square root, so here we'll just square both sides of that equation to get rid of the square root. And the other thing I'm going to do now is to save myself a step, is I'm going to start expanding these, because clearly I'm going to have to expand them in order to continue simplifying this equation. Okay, so it's just squaring binomials, nice and easy. So here we have x squared minus 4x plus 4. And the second one we have y squared plus 2y plus 1. And here we have plus z squared minus 6z plus 9. Okay, again, something that you should in principle be able to do nice and quickly. So here we have x squared minus 2x plus 1. Y squared plus, minus 4y plus 4, and then here we have z squared plus 6z plus 9. Okay, and I hope you kind of see something really nice going on here, because all the squared terms just cancel each other out, because you just subtract them from either side of the equation, and so now I'm left with something significantly simpler. Okay, so here we've got negative 4x, and I'll bring over plus 2x, so I'm left with negative 2x. Here I've got 2y, and this is going to be plus 4y, so plus 6y. And here we got negative 6z minus another 6z, so minus 12z. Okay, and then here let's do the constants. So 4 plus 1 is 5, plus 9 is 14. So 14 minus 1 is 13, minus 4 is 9, and then minus another 9. We just end up with 0. So we're just going to have this equation here. Okay, so this is the equation okay, because that's as far as we can go in terms of simplifying. So we clearly can't solve this equation, meaning there's more than one answer. So this represents all possible solutions. That's the relationship between the three variables. Okay, but now in B, they want us to find two such examples. Okay, now I'd say that there's one that just by inspection you should be able to see, because you realize if x, y, and z are all equal to 0, well, that combination is just going to equal 0. So I think I can just do that one by inspection. 0, 0, 0. Question is, how am I going to find another example? Well, I've got three variables, okay, in one equation. I can only solve for one variable. So what I'm going to do is I'm going to choose two of the variables. So I'm going to say let y equal 1 and let z equal 1. Pick something easy. And now I can solve for an x value. Okay, so I'm left with negative 2x. Okay, plus 6 minus 12 equals 0. So negative 2x equals, well, 6 minus 12 is negative 6. Bring it to the other side, becomes positive 6, so x is equal to negative 3. So my other point, or one other point, could be negative 3, 1, 1. And I can do a whole bunch of those. You know, I can pick an x value and a z value, solve for y. Pick an x and a y, solve for z. Okay, so it looks like there's infinitely many solutions. These just happen to be two of them. Okay, so just to do a quick recap, step number one was to set up the problem. As I have 2 points and I'm looking for other points, so I pick some random one, okay, such that the distances are the same, okay, but I see the distances as the magnitudes of these vectors. And then from there I just use my definitions to get to as simple an equation as I can get to. Okay, that's it for this one.